In this video we're going to be looking at wheeled robots, which is a class of mobile robots that are very, very commonly used and probably the most widely used outside of what we'd use in industrial settings. We've got a few different varieties of wheeled robots and a few different varieties and configurations of how we use the wheels and what type of wheels we use. So we have our fixed conventional wheels, our steerable wheels, our caster wheels, and our fixed omni wheels. So let's go through these in a bit of detail. Probably the simplest system is the fixed conventional wheels, where we have a wheel that can only rotate on one axis, and that's the axis that goes straight through the center of the wheel. So essentially it rotates the wheel and makes the wheel move. This wheel is somehow rigidly connected to the chassis so that it can't move back and forth. It can only move on this axis. It might be driven directly by the motor, as in the picture that we've got there, or it might be that there's some sort of a chain or belt arrangement from the motor or another gearbox that drives it. The important thing is that wheel can't turn around or anything like that. It can only turn on the axis that it's actually being driven. So these are commonly used for the main drive wheels of mobile robots. Our next wheel is the steerable wheel. And the steerable wheel adds an extra element of rotation to it. So the steerable wheel can turn as it makes contact with the ground surface, just like the fixed wheel that we had earlier, but it can also be steered. So we have a second axis of rotation that passes through the center of the wheel and allows it to rotate with respect to the chassis. We notice it goes through the center of the wheel, and we can steer this and actually control it. So we can say we want to change that wheel to be this particular angle or this particular angle. One place we'd see this is, for example, on a tricycle or the robot that we have here, where we have that front wheel being actually steered and controlled. We have this sort of thing on motor cars as well, where we typically have our front two wheels, or for something like a Reliant Robin, we have only one front wheel, and we can control that wheel and steer it around and point the car in the direction that we actually want to go. We then have something that's slightly different. We have a caster wheel, and this caster wheel is essentially designed not to be a steerable wheel like we had before, but a wheel more for stabilization and less for being able to actually control what direction it's pointing in. So once again, we have one axis allowing the wheel to rotate, like in the fixed wheel, to roll along the ground, and the other wheel, we have another vertical axis that's offset from the center of the wheel. And having this wheel offset rather than going through the middle of the wheel will cause this wheel to swivel and follow the direction and align itself with the direction of motion of the actual robot. We have these sort of things to balance the robot, to balance the chassis of the robot and stop it tipping over. For example, we might have three wheels in our robot, two drive wheels and a little one of these caster wheels at the front, and that will stop the robot falling over. These are commonly used in shopping trolleys, the front two wheels in shopping trolleys, front two wheels in wheelchairs. They provide stabilization, but don't actually allow us to control where we're going. We don't steer these wheels in a particular direction. And finally, we have omni wheels. Omni wheels, and there's multiple different configurations of omni wheels, are a special wheel because they're essentially a wheel which has wheels within inside it. These multiple wheels, what we do is we mount them essentially in a fixed orientation with respect to the chassis. We bolt them on and they can only turn in one direction. But with these small wheels inside them, they allow them an off-axis rotation. So this wheel can happily turn in this direction, but can also happily move in this direction and just roll along there. Now these aren't quite as widely used, but what we can use them for is to create a robot that can move in any direction at once, where it doesn't need to turn into corners. So rather than a normal robot, we'd have to do this sort of thing or turn like this and go this way. This robot can directly go this way or this way or this way or this way. It can turn, or it can just go straight off like that at a particular angle. It can go pretty well wherever it needs to go. Having discussed that, let's look through a few of the different drive mechanisms. And here's the typical drive mechanisms that we use within mobile robotics. Our first one is what we call differential drive. In differential drive, we essentially have two fixed wheels, each directly connected to its own motor. Either directly connected or through chain or belt drive or something like that. And we might use one or more caster wheels or even an omni wheel or something at the front, like in the picture that we have here. And that's basically to provide stability, to stop the robot from falling over. Odometry in this regard is very, very simple. We just use in one of the previous lectures the encoders that on each wheel. Left wheel has an encoder, right wheel has an encoder, and we measure the distance of the left and right wheel and measure where the robot's moved. Our steering is based on the differential speed of these two drive wheels. So we make one go faster, one go slower, and we can turn in a particular direction. Our next one's tricycle steering. And essentially we have two fixed wheels at the rear and a steerable wheel at the front. And that steerable wheel allows us to change the robot orientation. If you've seen kids' trikes, they essentially have a similar sort of thing. Kids can steer the front area and allow that to control where they want to go, and then they provide some force to get them going. Now, one thing that we need to note is when turning corners, the rear wheels will need to turn at different speeds. Essentially, because as we go around a corner, the inner wheel covers less distance than the outer wheel, and hence the outer wheel needs to turn at the fastest speed than what the inner wheel needs to do. A few different ways we could do it. We could, if the rear wheels are being driven, we can have a differential joint to allow them to distribute the traction between the two wheels. Or our front steerable wheel can be the drive wheel as well as the steering wheel. And our rear wheels can be essentially free spinning wheels that just turn and allow us to move. Typically what we'd do is on our steerable wheel have both an incremental encoder and an absolute encoder. We'd have an incremental encoder to measure how far that wheel is actually turned, and an absolute encoder to allow us to determine what the angle of the wheel is with respect to the robot chassis. Our next type of steering is Ackermann steering. And Ackermann steering is what we'd commonly find in motor vehicles. Essentially, we have two fixed wheels that are driven by a single motor at the rear or at the front, and they provide the drive force. We need some sort of a differential joint to allow them, once again, just like in the tricycle drive, to supply those so they can turn at different speeds. We then have two front steerable wheels that are connected to each other via a 4-bar linkage. And that 4-bar linkage allows and is configured to allow the robot to turn those wheels at the right orientation, with the wheel on the inner side of the circle actually turning at a sharper angle than the wheel at the outer side of the circle. What we essentially do when we're computing this is create an imaginary wheel halfway between our left and right steerable wheels at the front and turn this into a tricycle problem. So we've got the formula there based on the track width and the wheelbase and the inner wheel angle. We can compute this for the outer wheel angle as well if we want to, and we'll get exactly the same result to give us the angle for our imaginary wheel, theta SA in this case. Another method of locomotion is using skid steering or tank steering. This is often called because a lot of tanks will have this sort of steering mechanism where we'll have some drive wheels and probably multiple ones, but then some big tracks that go through right along them. And essentially we apply differential drive between these two tracks and allow us to steer around where we need to go. Now, these are pretty well rubbish to do with odometry because we're essentially relying on the kinematic realities of slippage occurring. When we're turning on the spot, we're relying on a huge amount of slippage occurring between those two wheels to move us about. And there's a huge area that we're trying to do that over as well. These are commonly used though in bulldozers and tanks and ruggerized teleoperated robots like the PackBot 510 up there. These are very good for rough terrain and getting over all those bumps and things like that. And some models like this one, which has an articulated second set of tank treads as well, allows it to drive directly upstairs and encounter all sorts of difficult terrain. And that brings us then to the Omni wheel. So typically we'd have a 3-wheel Omni wheel configuration where we have 3 Omni wheels configured in a triangular sort of situation. Rather than our previous examples where we need to turn into a corner to work out where we need to go, Omni wheels can move it in any direction at once without turning. And we call this holomonic. Essentially, the controllable number of degrees of freedom is equal to the total number of degrees of freedom. In this case, we have 3 degrees of freedom. We can move in this direction, we can move in this direction, and we can rotate like this. Now, for another robot like a differential drive, we also have 3 degrees of freedom, but we can't control all those degrees of freedom. We can't generally move directly like this, but we can move like this, and we can rotate. So the way this looks diagrammatically, we have these 3 omni wheels that are mounted at 3 points of an equilateral triangle. These provide us with stability and allow us for direct rotation and movement in any direction that we want to go to. For example, if we want to go directly forward or up in the slide here, the motor at the bottom, motor C, or with the force C associated with it, remains stationary. And the other 2 motors propel the robot forward, and the inner wheels will be slipping against each other as the robot goes up and as it goes forward. If we want to turn on the spot, we turn all the motors in the same direction and allows us to turn on the spot, for example. There's different configurations of these, so we can have 4 omni wheels or even more omni wheels. This is the most basic form and does a fairly decent job. Now, in terms of plotting a direction of where we're going, we can easily work out a vector of where we want to go and work out the differential speed required to drive each of those modes to get us in that direction. So here we plot a vector ft, which is corresponded to the red line there, and that's made up of vectors resultant from each of those wheels, FA, FB, and FC. We can very easily work out what FA and B and C are based on the angle that our vector relates to. One thing to note though is these aren't particularly good for odometry because by nature, with all these little wheels inside them, wheel slippage is something that has to occur to actually make this even possible. Getting back to odometry for a moment, one thing that we notice is there's 2 types of errors that can occur when we're using wheel odometry for navigation. The first type is systematic errors. And systematic errors essentially occur when we've got unequal wheel diameters between the 2 wheels. Remember back in when we were calculating the distance travelled by a particular wheel based on the number of encoder counts, the nominal wheel diameter was a key variable in there. Now, if our wheels are significantly different inflations, or we've got an old wheel and a new wheel, and the old wheel's significantly worn and it's a different wheel diameter from the other one, that will cause us issues. We've got problems when the real wheelbase differs from the nominal one. So we might have wheels that are flat wheels and they're an inch wide for sake of the argument. Where do we measure the wheelbase between that wheel and that wheel? Is it the inner part of it? Is it the outer part of it? Is it the center part of it? What about if the wheels are slightly misaligned with respect to the chassis? One of them's 1 degree off when it's been mounted on there. Well, all these things can cause systematic errors. We've got a number of non-systematic errors as well. So when we travel over uneven floor, slippery floor, when we over-accelerate and start skidding or start doing wheelies and things like that, all those things are much harder to characterize and harder to compensate for. So essentially our systematic errors are ones that are prevalent over smooth ground. They constantly accumulate and lead to larger odometry errors, but they're things that we can compensate for and correct for. But over rough ground, when our robot's bumping around and going in all sorts of different directions, our non-systematic errors tend to be more frequent and hence contribute to the bulk of our odometry errors in that sort of circumstance. One interesting thing that we get is these error ellipses. Our uncertainty about where our robot is, and our uncertainty related to the error that's occurred, increases over time and increases in the shape of an ellipse. And if we think about this, our odometry does reasonably well at telling us how far we've actually travelled. And that's why we see as the robot moves along, the distance we've actually travelled, we've got a reasonably good idea of it. The orientation of the robot is what really grows that ellipse out. And the orientation is completely governed by small changes between the left and the right wheels. And so we can very easily head ourselves off in one direction, and though we know pretty well how far that we've actually travelled, our pose may be significantly off because our orientation's been off. And that's why the ellipse is biggest in that direction. Now, one way that we can actually calibrate our robots is doing some testing. And one common test that's used is called the UMB mark test. And basically we need a fairly wide area, and the idea is to try and remove some of those systematic errors. So we have a 4 meter by 4 meter square, and we drive the robot round that square 5 times, and then we do it 5 times in reverse. Each time we do it, what we want to take note of is the finishing pose, so the position and orientation of the robot. So here's an example of how we can perform the UMB mark test. So we run the robot, and at the end, we're expecting, unless it's been calibrated really, really well or is amazing, our robot won't be right at the start point again. It will probably have an error both in the X and Y direction, but also in the orientation. And so we can use that to work out, we might have not turned at 90 degrees, for example, but turns at 93 degrees. And this might be an error due to the effective wheelbase. Our wheels were an inch thick, and where were we actually measuring on that? Well, we can use this to plug it back in and correct our effective wheelbase and say, well, if I made the effective wheelbase this, I would have turned at 93 degrees, which is what I've found has actually happened in reality. Once we've done this, we can use these values and correct for them and significantly improve the odometry for our mobile robot.